this new IceCube upgrade. We're expecting this new IceCube upgrade detector in a few years' time, and one of the main motivations to do that is to study neutrino oscillations. So, what I'm going to try to do in this talk is give a bit of background on why exactly we study neutrino oscillations and why a telescope at the South Pole is actually a good place to do that, and then hopefully that will be somewhat convinced at least that it's an interesting area of research, and you start to understand also why we need to really start to increase the precision and our capabilities with the IceCube upgrade. So I'll go ahead and get started just with a quick introduction to why we have this fairly strange detector in the first place. So this isn't really directly related to oscillations, but it's kind of the story about how we came to have this detector. So the Earth is constantly bombarded by cosmic rays, as I'm sure most of you know. What people don't always realize is these can have truly colossal energies, up to even EeV, way beyond anything we can produce on Earth. And it's been a long-standing mystery about where exactly do particles of such incredible energies come from. Now, the general consensus is that they're believed to originate in very violent events in the distant universe. So things like generally systems where something like a huge supermassive black hole consumes an entire galaxy, converts that energy into relativistic jets, and these jets fire particles at unimaginable energies across the universe, where some of them will eventually intersect the Earth. And as well as propelling, for example, protons to make cosmic rays, these jets will ultimately also produce, for example, gamma rays and neutrinos. And so there's a whole burst of different particle types coming from these extremely violent events that are potentially detectable. And this comes to the idea of multi-messenger astronomy. And so cosmic rays are one of these things we see many of them, want to track where they come from. But the problem is they're charged and they're deflected by magnetic fields. And that means they don't travel in straight lines, even through essentially empty space. And what that means is that we can't really track them back to their source. But we have these other types of particles, maybe they can help us. We see a lot of gamma rays from distant sources, but the problem with gamma rays is that although they're not deflected by magnetic fields, they still experience the electromagnetic force, and ultimately they're absorbed at high energies. So if you want to look at something very far away at very high energy, gamma rays are also not necessarily the best option. Neutrinos, on the other hand, can really traverse the entire universe essentially unperturbed, because they only experience the weak interaction and gravity. And so if you see a neutrino arrive at Earth and you believe it came from something astrophysical, you could literally trace its path back across the entire length of the universe to see what it came from. And so that's the motivation for using neutrinos in the studies of trying to identify where these things are in the universe. But then the question is, how do you detect these neutrinos? I mean, neutrinos are notoriously hard to detect. They have these tiny cross sections. That's what makes them good messenger particles, but it also means they're hard to detect. And we're talking about TeV to PeV scale particles here, so very, very energetic particles. The general way people try and do this sort of thing is they, for example, fill a huge tank with some sort of liquid. The idea then is the neutrinos enter the tank, a small number of them interact and produce charged particles, and those charged particles produce Cherenkov radiation within the liquid, and then you detect that with PMTs. And that's, for example, how Super Kamiokande operated, which is a very famous experiment from Japan that you can see in this picture here. It was used to originally identify neutrino oscillations along with the SNO experiment. But of course, that was a detector of a certain size. It already seemed pretty big at the time, but theoretical estimates of how large a tank you'd need to detect the astrophysical flux, given kind of rough, back of the envelope calculations of what the flux might be, suggests you need roughly a cubic kilometer size tank to detect even a handful of these astrophysical events per year. Not to mention you need something large just to contain a PeV scale event, which is depositing light across kilometers or so. And just for context, that's about 20,000 Super Kamiokande. So it's not seeming that easy to scale up that kind of detector. But there is a solution to this, and that solution is to instrument a natural medium. Rather than build a tank and fill it with something, you just find something that's naturally there and transparent. And conveniently, the ice deep in a glacier is extremely transparent as the high pressure forces out the air bubbles. And also conveniently, there's a base run by the US Department of Energy at the geographic South Pole, which happens to be sat on top of a 3-kilometer deep glacier. So that seems like a good place to maybe build this sort of thing. And that's exactly what IceCube is. So in this 3-kilometer deep glacier that's at the geographic pole, what we do is we drill holes down into the glacier, and drill really means melt in this case. We melt these holes down. They go around about 1.5 kilometers down of just nothing essentially to get down to the really clear ice. Then at this point we lower down strings, and each of these strings is basically covered with each of them has many of these PMTs surrounded in these pressure vessels with readout electronics called DOMs. And so we have 5,000 of these digital optical modules instrumenting in total a cubic kilometer of this glacier below the surface. And that's about a gigaton of active volume, so absolutely huge detector. And this gives us the scale that we need to detect these astrophysical particles. What we also have in this detector, which is perhaps less well known, is that we have a region in the sort of deepest central ice where it's purest, called deep core. And in this region, the PMTs are packed much more densely, and this lowers our energy threshold and allows us to do physics at the GeV scale. And we do a lot of other types of physics apart from astrophysics with this detector in particular. Okay, so that's roughly the story of IceCube and how we got to have this very unusual detector. So now we have this extremely large detector, which is a very powerful astronomy machine, essentially a telescope. We can also ask the question, can we use it for particle physics as well? Can we exploit this unique detector for something else? And the answer is yes. And there are actually a few ways we can do this, but the way I'm going to talk about today relates to using another product of cosmic rays, which is atmospheric neutrinos. And so when these cosmic rays bombard the Earth that I mentioned right at the start, these interact high up in the atmosphere and produce air showers of many particles, for example, and you end up with a flux of essentially muons and neutrinos at the ground level. So that you have a constant flux of atmospheric neutrinos, which for an astrophysicist are an annoying foreground to their astrophysical searches. But for particle physics, this is actually a copious, very high energy, and for the most part, relatively well understood neutrino beam. And with a detector the size of IceCube, that means we can detect at a 10 millihertz rate. So every few minutes we can see a neutrino from this source, essentially. So this is a really powerful neutrino beam that we can try and do particle physics with. So how does this look in terms of what we see in the detector, and what's the phenomenology of these atmospheric neutrinos? So first we have the cosmic ray impact into the atmosphere and produce these showers of particles. You get mesons such as kaons and pions produced, they decay, and eventually you end up with leptons and charged leptons and neutrinos. So let's say we have an interaction up here. This neutrino is produced in the atmosphere. This is at lower energies, this is roughly a 2-to-1 mix of muon and electron neutrinos, and at higher energies, this increasingly becomes muon neutrino dominated, and there's a very small contribution of tau neutrinos from heavy meson decays. After that neutrino is produced, it starts to propagate across the Earth, and it's a neutrino, so it can in general penetrate the Earth and move right across, for example, to the detector. And a few different things can happen to this neutrino as it propagates. What you can see here is a plot of the probability of a muon neutrino surviving as a muon neutrino as it crosses the Earth. This is the arrival direction. So up here, this is neutrinos coming from above the detector like this. And down here, this is neutrinos coming from the opposite side of the Earth. And in the middle of this plot is particles coming from the horizon like this. And what you can see at the low energies, the sort of the GeV scale here, you see these bands of strange behavior, and this is neutrino oscillations. So what you're seeing here is these muon neutrinos disappearing to other flavors. And this is, for example, also what was measured by Super Kamiokande, but down at the lower energies down here. The other main piece of phenomenology you can see here is that at the higher energies, we actually have an Earth absorption effect. And what's going on there is that even though you normally think of neutrinos as not interacting, at high enough energies, their cross-section becomes large enough that they can't actually penetrate the Earth. So once you're getting up to around the 10 TeV, 100 TeV sort of level, neutrinos can't actually penetrate the full Earth, and you have a depletion of your flux for that reason instead. Those neutrinos that do make it to the detector, some fraction of them will interact within the detector volume, and for example, will produce charge mainly via deep inelastic scattering interactions and produce charge secondaries. And those charge secondaries will produce Cherenkov light in the detector. There's both track-like events where you have a high energy muon produce an interaction, producing like a long track through the detector, And you also often have a cascade component that where you have a more spherical-like emission, which comes from, for example, electron showers, tau showers, or just from the breakup from the nucleus itself. Just to give a bit of context of what you see in IceCube itself versus the deep core subarray. So in the IceCube detector, you're mainly looking at TeV scale neutrinos. So this is this part of this plot here. So you see with the main IceCube detector, you're not really seeing these oscillations, but you are seeing these Earth absorption effects. So you can actually use these Earth absorption effects to measure cross sections and also search for BSM oscillations. And here you're seeing very bright kilometer scale events here. Probably this is the kind of images you're used to seeing from IceCube. As a contrast, for in the deep core array, we're seeing these GeV events, so the order sort of 10 to 100 GeV here, and we do see an appreciable fraction of this oscillation pattern in this energy range. We detect all neutrino flavors, but the downside to using this low energy detector is there's of course a lot less light from these low energy events, and so the kind of events we see look like these kind of events. So a far cry from the kilometer long tracks that people often show in IceCube talks, but still these are things we can detect and reconstruct. And these are the kind of events we use for oscillation physics. So a bit more on the neutrino oscillations themselves. So many people here, I'm sure, are familiar with this, but I'll give a quick primer. So the fundamental idea behind neutrino oscillations is that neutrinos propagate not essentially as a single quantum state, but as a superposition of free mass eigenstates. And each of those mass eigenstates actually evolves at a different frequency. And that frequency is defined by the mass of each of the free states. Now, the other piece of this puzzle is that as well as being this the superposition of free mass states, there's actually a mixing between the mass states, which is the propagation states, and the states in which the particle interacts, which are the flavor states. And so what that means is you're really a superposition of the free mass states, but also a superposition of these free flavor states. And because of the time dependence of the propagating states, what you then have is a time dependent superposition of flavor. So essentially your flavor component is time dependent. And ultimately what this means is that if you produce neutrinos one flavor in an interaction or a decay, say a mu neutrino, it has some probability of being detected as a different flavor at some time later, not because it has changed flavor necessarily, because it always had these components of the different flavors, and a different one is now at the peak of its wave function essentially. And this is what we mean by neutrino oscillations, and it's a very interesting phenomenon. It's given rise, for example, to the observation that neutrinos must be massive, or else these oscillations can't take place, which is one of the only known examples of beyond standard model physics. And in general, this is also one of the only known places where we can study a quantum system at macroscopic scales. The basic phenomenology of neutrino oscillations are that the mixing between the flavor and the mass states is characterized by a complex 3x3 matrix known as the PMNS matrix. But this is normally parameterized by free mixing angles and a CP violating phase. So you have these free angles, theta 1, 2, theta 1, 3, and theta 2, 3, as well as the CP violating phase. And the question of whether CP violation takes place in the neutrino sector is an extremely important one, though it's not one I'll touch on too much here because it's an area that at this time IceCube just can't really make any statements about, but it's one of the main goals of the accelerator community. The oscillation frequency itself depends on the mass difference between the mass states. No, so not directly on the masses, but the difference between the masses, because it's a superposition effect. So it's the difference between the wave frequencies, basically. And so in total, you end up with these 6 parameters to measure. And so this is essentially the job of the global neutrino oscillation program, be it reactors, solar accelerators, atmospheric, etc., is to measure the values of these 6 parameters. And the basic phenomenology of how the oscillations depend on these parameters are, in the simplified 2-flavor case, that's the amplitude of these oscillations defined by the mixing angle, whereas the frequency is defined by a combination of the mass these mass differences, and also by the energy and the baseline or the travel distance of the neutrino. So these are the parameters we're going to need to, if we want to measure oscillations, we're going to need to measure the oscillations. We're going to need to measure the baseline, the energy, and by doing that, we can infer the mixing angle and the mass splitting. So what exactly do these look like in deep core? So if I focus on the energy region of interest, which is roughly from about 5 GeV to about 100 GeV, this is about what we're able to observe in deep core. In this particular energy range, what we're really observing is the atmospheric mixing angles, so θ2 and delta m32 squared. So the same parameters, and these are actually the same parameters that we measured by accelerator experiments. And we actually observe a near maximal transitions of nu mu to nu tau for neutrinos that come up through the Earth and cross the whole detector. So for downgoing neutrinos, they don't travel far enough, but for upgoing neutrinos, they travel long distances up to about 12,000 kilometers. And at these energies, they will maximally oscillate to tau neutrinos. In terms of how that affects what we see in the detector, if your mass splitting changes here, this essentially shifts this pattern or compresses this pattern left and right. So it's basically changing the frequency of this pattern. Whereas if this mixing angle changes, you're changing how strongly they disappear. So essentially the color scale on this plot, how deep these oscillation values go. And so to measure these effects, we need to measure the energy, the arrival direction, which is a proxy for the baseline, and the detected flavor, or some proxy for it again. So in terms of what we're actually measuring, of course, we don't know exactly the true information about the neutrino. We can only measure what we can reconstruct and observe. So ultimately what we measure is 3D distortions in our reconstructed energy zenith, which is angle, and PID dimensions. How this looks essentially is if you combine just the oscillation effects, we have to combine everything we see in the detector. So we have an initial flux. This flux then oscillates. We then undergo the interactions in the ice, and then ultimately we have the effects of the detector, the readout electronics, etc. And we put all those pieces together, and we ultimately end up with a flux of neutrinos in the detector that looks something like this. So in terms of the true energy and the true arrival direction, you have a mule neutrino flux that looks something like this. The flux is most strongly peaked around the horizon here, and then it is initially roughly symmetrical above and below the horizon, but because of these oscillations, you have these clear depletion regions, and this is exactly what the oscillation effects we're looking for is. And you have these mule neutrinos disappearing, and if you look at the tau neutrino channel instead, what you see then is an appearance of tau neutrinos in exactly the energy region where you're losing neutrinos from the mule neutrino case. And that looks great. You see these very clear bands, but of course this is using true parameter, the truth information. But what we can really do is reconstruct these parameters, and you end up with seeing something that looks more like this, which of course is a much less compelling image, but that's the reality of using a sparse detector. But even in these reconstructed, even in this reconstructed space, you can still by eye make out this this depletion region here, for example, where these oscillations are taking place. And so ultimately what we're measuring in these patterns here and doing a likelihood-based analysis to essentially measure this depletion region and the corresponding appearance in the cascade channel. So I've introduced here a little bit how we measure oscillations in deep core and what oscillations are. Just we're far from the only people who measure oscillations. So just to give a bit of context for why deep core's oscillation program is interesting and what its limitations are. So its strengths are that it is extremely high statistics detector compared to most neutrino oscillation experiments, because it's just so large, because the flux is so high, and also because it's a high energy where the cross sections are higher. I'll give some context of what those numbers are shortly. Another big advantage is it can detect tau neutrinos, which most experiments can't, and I'll come back to that later. The high energy, the large baselines, the dense matter involved in the neutrino propagation gives a lot of sensitivity to BSM physics, which is not always possible in other experiments. IceCube is particularly good at the BSM side of oscillations. And we also have a nice advantage that the energies we operate at, we're mostly observing deep inelastic scattering interactions, which are much theoretically simpler than, for example, quasi-elastic and resonance cases, which for example, is the main channels in the accelerator community. And these are a lot harder to handle theoretically. And this is all essentially very complementary to accelerator programs, because we're measuring the same parameters, but at 10 times the energy with totally different uncertainties. So if we get the same results as accelerators, this is again, very compelling evidence that we have the right model. For weaknesses, probably the single biggest one is that we have a natural detection medium. It's not a finely tuned detector of homogeneous scintillator or something like this. It's glacial ice. It's been deposited over tens of thousands of years, and we have to calibrate this, including various bands of volcanic ash and this kind of thing. So we have to work very hard to understand our detector. We also the detector is also very sparse compared to an accelerator experiment. So we only observe a tiny fraction of the light. And what that means is that we have a poor resolution compared to what we common in an accelerator experiment, or even something like Super Cameo Candé. And of course, there are large uncertainties in the atmospheric neutrino flux, although these are mostly well handled now. And there are very large backgrounds, for example, of atmospheric muons and also of detector noise. And the final weakness, when you contrast to for example, an accelerator program, is they normally feature a near detector, which allows them to measure the neutrino flux and cross sections before the neutrinos oscillate. We don't have that, of course. We don't have something up in the sky, but it is worth noting that this weakness is partially alleviated by the fact we also detect downgoing neutrinos which are unoscillated. So we have sort of a near detector in that sense as well. Okay, so that was a bit of an overview for what our measurements are and why we're doing them. So now I'll go on to what the latest results actually are from these. So we've been working for the last about 5 years now, I think, on a new generation of oscillation analyses, this has been a huge collaboration-wide effort now, as opposed to some of the earlier work we did, which was different groups did independent things. It's now one consolidated effort across the collaboration. We've accumulated 10 years of data now with this deep core subdetector. So this is very high statistics. And in terms of what we're actually measuring with, this gives us around 210,000 neutrinos to work with for the current measurements, which when you compare to, for example, an accelerator experiment, they're probably talking about around 100 events. So much higher statistical power than accelerators, albeit, as I mentioned, with lower resolution and more difficult calibration, etc. We also have only 0.7% background, which is atmospheric muons in these data samples. So it's high statistics, but it's also very pure. As opposed to previous generations of measurements, essentially every element of the analysis chain has been rewritten and updated. Our calibration is much improved from what it was before. We have far more systematic uncertainties considered. We have brand new simulations, brand new methods for background rejection and reconstruction, etc. So essentially, it's a total reworking of everything we do for our oscillation measurements, which is why it's been such a long, as I say, 5-year effort. And in particular, there's been a lot of focus on making the analyses robust to systematic uncertainties, because we have a lot of statistics. We're becoming systematics dominated, and we are in a natural detection medium, etc. So we do as many things as we can to reduce our dependence on things that are hard to measure about the detector. So, for example, we build charge-independent data samples, so we don't have to worry too much about our PMT calibration. We try to include as many off-signal regions, like the downgoing region, in the analysis to help constrain systematics separately from the oscillation signal. We've been exploiting data-driven background methods, so we don't have to rely completely on simulations and these kind of things. So yeah, ultimately the data sample we end up with after we've been putting all this work together requires a number of pieces to be pulled together. So first, we have to remove the backgrounds that are present in our sample. So although there's plenty of muons in our detector, there's far more atmospheric muons and coincident noise backgrounds in the detector. So if you look at this plot here, for example, this shows the filter level, which is something akin to a trigger level in the detector. Initially, there are, about 3 orders of magnitude more background events, so from muons or from noise in the detector, than there are from neutrinos here. And this is even after going through triggering and filtering. So before that, it's even worse. But by the time the data comes through the kind of standard sort of readout, we have about 3 orders of magnitude more background than we do signal. So we have to work very hard to remove that. We have a number of processing levels. So you can see here as we move along, this is each a new stage in our background rejection procedure. And what you can see is by the end of this process, we've managed to reduce our noise events to essentially 0. And our muon events have also been suppressed by about 6 orders of magnitude, to the point where they're only 0.7% of the sample. We also lose some neutrinos as we go down this process, although it's worth noting that quite a lot of these neutrinos are uncontained and not really suitable for physics anyway, so we can't measure their energy reliably. And so ultimately, by the end of this process, which features a number of different machine learning methods, as well as more sort of traditional cutting methods, we end up with this neutrino-dominated sample with around a millihertz total rate. The other thing we need to do once we've got a pure sample of neutrinos is we need to then reconstruct the properties of that neutrino. As I showed earlier on the talk, we need their energy, their direction, and we also need to understand their flavor. We have a number of different methods for doing these reconstructions, and we're actually we are going to, for the oscillation studies, we're going to produce multiple results using different reconstruction methods to make sure that they're consistent, to make sure that we have a reliable result. For reconstruction in particular, we have two main categories. So we have the first is a likelihood minimization procedure, where we essentially fit the neutrino properties compared to pre-computed expectations from simulations. And this is the traditional method. It's very reliable, but it's also very slow. And increasingly now we have a lot of machine learning based techniques. So extreme gradient boosted decision tree ensembles for classification, and convolutional neural networks, and more recently graph neural networks for our neutrino reconstruction. And you can see an example here of how we're reconstructing our mule neutrino events. This is the true energy of the event. This is the reconstructed energy, and you can see it reconstructs pretty well on this one-to-one line here. So, and with an angular, with a sort of an uncertainty here shown by this 1 sigma error band of about 30%. So we're now moving into a systematically limited regime with these measurements. So we have to take a lot more care in systematic uncertainties than maybe we did in the past. And so there's been a huge amount of effort the last few years to really expand our treatment of these. We have three broad categories of this. The first is the neutrino cross sections. We have three channels we're observing essentially: the resonance events, quasi-elastic events, and predominantly deep inelastic scattering events. And we have various ways of computing uncertainties for these. I think for the DIS in particular, we do things like comparing different models, so leading order, next to leading order models, and especially trying to manage a difficult transition region between next to leading order effects that calculations are only valued at about 50 GeV compared to leading order calculations that are only valid at the sort of GeV scale. So we have some interpolation between these methods with uncertainty. And we also work to, for example, propagate the PDF uncertainties to DIS cross sections, which helps us evaluate uncertainty in something like tau neutrino cross sections, which there aren't really a lot in the way of actual measurements for. For the neutrino flux, we have to account for the uncertainty in the primary cosmic ray spectrum and also in the hadronic model uncertainties itself. The primary cosmic ray spectrum is actually getting pretty well tied down now with lots of data from many experiments such as AMS and the International Space Station. So this is actually known pretty well now, but there are still large hadronic model uncertainties. This is a lot of this, even in the LHC area, we have large uncertainties in this. And this is mainly because the energies we're talking about are very high, and we're also talking about the very forward part of the parameter space. So this is stuff that that in the interaction goes straight down the beam pipe of the LHC. So there's still not an awful lot of data to actually constrain the parameter space of hadronic interactions that we're interested in here. So there's quite large uncertainties in this. The way we handle this is we use a nice tool called MCQ, which is a very fast way of solving a cascade equation to recompute flux on the fly for a given primary flux and for a given hadronic model. And then we're able to basically tune individual parts of the hadronic space and recompute the flux live as we fit in our analysis. And that gives a lot of degrees of freedom to really have very conservative uncertainties on this flux. And finally, and most importantly for IceCube, we have the detector and the ice properties. For this new generation of analyses, we have individual charge calibration for every single PMT, which has made a big difference. We've also really evolved our modeling of the ice, so it's both its stratigraphy as you move down in layers, which you've got regions of which are dustier than others, comparing to various bits of atmospheric activity over the last 10,000 years or so. We've also increasingly understood or discovered anisotropy effects in the ice. So in particular, we're discovering that the flow of the glacier is not totally static; it has a very slow flow. And over many years, this has produced kind of a structure in the crystals that produces birefringence effects, which means photons don't actually travel in straight lines in this ice, which is somewhat counterintuitive. And these are effects that we've only started to account for recently in a really improved data Monte Carlo agreements. These seem to be real effects. And we to actually account for all these things in analysis, we essentially generate many different scenarios with Monte Carlo, and then fit for each of our analysis bins, we then fit multi-dimensional hypersurfaces that allow us to continually parameterize between different cases. We also have to study, for example, there is radioactive background decay noise in our PMTs, and this is again something that we have to calibrate and treat with uncertainties. And so from our perspective, cross sections are actually the least important for us. So for accelerators, these are often one of the most important, but for us, partly because we're in the DIS regime and partly because we don't really see the details of interaction, we don't really care how many pions came out, we just see a blob of light, essentially. So we're mostly not too susceptible to cross-section effects. Flux, we have fairly large effects from, but we also have very conservative uncertainties here. And by far our biggest challenge is dealing with these detective properties. And in total, we now have about 40 systematic uncertainties in the analysis. So on to the actual results of this analysis. So before we move ahead to the final analysis with the full statistical power of the data set and all the sort of brand new shiny cutting edge methods, in 2021, we produced an initial measurement using just a small subsample of these events, which we called golden events. These were very clean events, very low levels of photon scattering, so they're not particularly affected by any uncertainties in the ice. So we made very harsh cuts to only get these kind of golden, really nice, clean events. And that allowed us to, reduce our dependence on the systematic uncertainties we were still working to model, and also meant we could use more simple tools for reconstruction of background rejection, a lot less machine learning, for example. So we went on to produce this initial result using these simple tools and robust assumptions to test everything we were doing and flush out any potential issues while we were still working on the main analyses. And you can see the result of that analysis here. This is this contour shows the 90% confidence limit of what we measured, along with the best fit point here. This is the mixing angle for our oscillation results and our mass splitting. And you can see that compared to a number of other experiments from the community. So here, this is Super Cameo Candy, this slightly strangely colored green line here. We've got the Minos slightly older accelerator experiment here. Then in sort of right in the middle here, the smaller, most precise contours coming from the T2K experiment and the Nova experiment here. And so you can see already, even with only this around 10% of the statistical power of our analysis, albeit some of the nicest events, you're getting already a contour that is very consistent with the latest accelerated results, and already starting to get into the same sort of ballpark in terms of actual precision. And as you can see here, we prefer our best fit point is very close to maximal mixing here. Just to give a context of how that result compares to previous IceCube results, we had two previous 3-year results, which 2 independent measurements by 2 different groups. You can see here, one was in orange here, one was in purple. They were both fairly similar in precision, and you can see our contour is already much smaller than those results, even using this initial subsample, which is really nice. You see also there was a mild tension in the mass splitting measurement between these 2 results, and the new results seem to be sitting nicely in the middle of these 2. You can also see here, this is a plot, for example, of our analysis histogram projected into the L over E space. And you can see here, very nice data Monte Carlo agreement here at our best fit point. And this dashed line here showed what the data would look like if there were no oscillation. So this lack of events is really our signal. So we're not doing the analysis in this 1D L over E spaces, in the full 3D L, E, and PID space. So that was our this initial subsample result, and so we've now been working on the full 210,000 event result using the full 10-year data sample, and all the events, both nice and less nice. And those results are wrapping up very soon. So the first one unblinded very recently, and so that result's going through the approval process now and will be published shortly. We're in this analysis, we include all neutrino flavors, state-of-the-art reconstructions and background rejection, and we're producing multiple variants of this result with different reconstruction methods. You can see here this orange curve is a result I just showed you on the previous slides here, And this red curve is what we're projecting our sensitivity will be, or this is what we expect our result to be with this new result, which hopefully we'll be able to show probably in a matter of weeks, actually. And you can see here this contour is reduced significantly in size due to the additional statistical power and the improved methods. And you can see here this really is now a contour roughly at the same scale as, for example, NOVA and T2K here. So I think for the first time, IceCube's oscillation measurements are reaching sort of comparable precision to dedicated accelerator experiments. So a quick note on so that was our standard oscillation measurement. Now a quick note on some of the other slightly more exotic things we can do. And the first of these is tau neutrino appearance. So as I mentioned already, most of the neutrinos we see in IceCube are mu neutrinos, and in deep core we see them oscillating from mu neutrinos to tau neutrinos for the most part. Now this is also what happens in accelerator experiments or in super Kamiokande, but the difference is that because tau neutrino charge current interactions are actually strongly suppressed by the actually very heavy tau lepton mass. What this really means is tau neutrinos can't even interact in the charge current channel until the neutrino is about 3.5 GeV and is strongly suppressed all the way up to about 1 TeV. And what this means is in most experiments, they are not even capable of seeing the tau neutrinos, whereas in IceCube, the high energies we operate at and the high statistics we have means we do actually see not just the disappearing of the mu neutrinos, but we actually see then the tau neutrinos appearing in their place, which means that we have two channels that we can measure together to check they're consistent. Plus, it also just helps us confirm the kind of free neutrino paradigm that these are really disappearing into tau. These are really converting to tau neutrinos, not something else that other experiments can't see, like for example stereo neutrinos. What this does is it allows us to kind of be more sort of trusting in our oscillation measurements, but it also allows us to make direct constraints on not just the mixing elements, but also directly measure the individual elements of the PMNS mixing matrix. And what that means is we can, rather than having to assume unitarity of the mixing matrix, we can provide these tau measurements, which are a crucial input to global studies, to actually fit the PMNS matrix directly and verify it is indeed a unitary matrix. Whereas, for example, if there are more than 3 neutrino states, for example, stereo neutrino states, then actually the PMNS matrix is not a 3x3, but it's a subset of an n by n, of which we're currently only aware of a 3x3 non-unitary sector. So tau neutrino measurements are really important to this, since they are in general far less precise than the electron or muon studies. So this large high statistics data sample I just showed our main oscillation expectation for, which, as I mentioned, is coming out very shortly. We're also using this to directly measure tau neutrinos. So this is essentially the same as the standard oscillation measurement, but the rate at which the tau neutrinos appear is allowed to vary independently from the actual rate of new mu disappearance. And so that means we're measuring the we're basically allowing ourselves to measure the two channels separately. And what we measure then is the tau neutrino normalization with respect to the free flavor PMNS or standard neutrino paradigm. And so what if we expect to measure a value of 1, if indeed the PMNS matrix is unitary. You can see here a number of measurements of this parameter in the past here. There's one from the super Kamiokande experiment here, one from the Opera experiment here, both broadly consistent with value of 1, mild tension from super K. And this is the previous deep core result using 3 years of data. You can see here with our expected result using the new 10-year data sample. And you can see here, this is by some way now this will be the most precise measurement of this parameter to date, around 11% precision of this parameter. And this is mainly because we have a very large number of tau neutrinos in this analysis, so about 9,700 in total. Whereas for context, there have only been about, if you exclude deep core data, there's only been about 200 tau neutrinos detected in total in all previous experiments. Okay, a few other oscillation-related topics beyond just the standard oscillations we're measuring here. So the first relates to the neutrino mass ordering. So determining the neutrino mass ordering is one of the main questions in neutrino physics, and it basically equates to answering the question, which is the heaviest neutrino mass state? Is it is the third neutrino mass state the heaviest, the normal ordering, or the lightest? And the reason we don't completely know that is because we are generally only sensitive to the size of these mass splitting, is not the sign. However, with deep core, we can actually exploit matter effects to try to probe this effect. And what you can see here is if you look at these oscillation patterns here, there's kind of a distortion effect here It's not just simple bands, there's a distortion effect here. And this actually comes from matter effects and is directly sensitive to the neutrino mass ordering, because this distortion effect affects neutrinos if it's the normal ordering, or antineutrinos if it's the inverted ordering. And so by trying to measure this effect, we hope to actually put constraints on or have some sensitivity to measuring the neutrino mass ordering. Since this is very close to sort of the bottom of deep core's threshold, currently we only have about 1 sigma sensitivity to this with a 10-year data set, but the upcoming IceCube upgrade will strongly improve on this, and I'll get to that shortly. I just want to very briefly talk about BSM oscillations, because IceCube has quite a few capabilities here. So as I already mentioned, we have these low energy oscillation effects here, nerve absorption here, but for most of the rest of this space, we expect no flavor transitions at all. So basically anything you observe in here is essentially BSM physics. And we can search this space for many different effects. Some of the ones we have measured in the past are, for example, searching for sterile neutrinos, and we've made a lot of useful constraints in the EV sterile space here. We can look for non-standard interactions for neutrinos, particularly crossing the core, as well as more exotic things like Lorentz invariance violation. You can see links to a number of papers on those here. I'm not going to go through these in detail here, but you can ask me about them afterwards if you're interested. But I do want to focus on one BSM topic in particular, which I think, in my personal opinion, is probably the most interesting, which is trying to put constraints on quantum gravity models. And so, as I'm sure most people know, currently we have no microscopic theory of gravity, and the only thing we do know really is that general relativity breaks down in small systems like black holes or the early universe, and we generally think we need a quantum theory of gravity. There's lots of ideas for this, string theory, etc., but none really yet that is kind of an accepted theory. All that we really know is probably that this is some high energy theory, and the standard model is the low energy limit of this. Now, the big part of the reason why this is such a challenge is because these effects are generally expected to only become large at the Planck scale. For example, 10 to the 19 GeV, 10 to the minus 35 meters, and these are generally things that are just very difficult to detect. So how do we even try to make measurements with those scales? There are ways we can try and search for Planck scale physics even without solid models, and the way we can try and do that is because quantum gravity theories typically often predict, or there are common features that come out of many of these theories. So, for example, modified or fluctuating structure of space-time, which is often called space-time foams, or violation of certain fundamental symmetries such as CPT, Lorentz invariance, equivalent principle, etc. Because neutrinos are essentially a macroscopic quantum system, or a quantum system propagating over macroscopic distances, we're seeing a quantum superposition that's traveling these macroscopic distances, and this superposition can actually be degraded or modified by space-time environments. So essentially, we can use neutrinos as little tiny interferometers as they pass through space-time to try and see if there are any anomalous effects. And IceCube is ideal for this kind of thing because we're observing very high energy neutrinos. This can partly, of course, nowhere near fully, but partly overcome any suppression in Planck scale physics with lower energies. We have very large baselines, even up to cosmological baselines, and so even tiny effects can potentially accumulate into something we could maybe measure. And with high statistics means you can start to search for subleading effects. There are a few different channels we can look at here, and I'm just going to briefly talk about one, which is neutrino decoherence. And this is one we have a very recent measurement of. So generally, neutrino oscillations we consider to be coherent, and what that means is although the neutrinos oscillate, the wave functions themselves are propagating coherently. So if you take two neutrinos of the same energy at the same place, and then let them travel in the same direction, the wave functions of both of those two neutrinos will evolve identically. However, if your environment is stochastic, so for example, you're traveling through some sort of fluctuating space-time, then they're going to become increasingly out of phase over distance. Now, of course, it might be a tiny effect if it's a Planck scale effect, but at the same time, over long enough distances, maybe it could accumulate into something measurable. There are many different ways in which neutrinos can lose phase coherence over long distances. So you can have light cone fluctuations from, for example, the space-time metric fluctuating. There can be interactions with virtual black holes, which are essentially, well, they're very exotic sounding. It's essentially vacuum polarization, but in the gravitational force. And the net result of this is something called neutrino decoherence. So essentially, your oscillations would expect to become damped over large enough distances. And this is something we can search for. We've been doing this recently with IceCube, and we've been doing searches both with our GeV and TeV scale neutrino data samples. And so searching for these damping effects, what the signal should look like depends strongly on what you assume about the energy independence, and we check many different cases. For an energy independent situation, you have your normal oscillations here and your earth absorption, but you can see a sort of a more general effect where you have these oscillations induced here by these additional flavor averaging going on, and you also have a degradation of your standard oscillation signal. On the other side, if you have more of an energy dependent case, which is probably more realistic for Planck scale physics, your effect only becomes strong at high energies. And here, for example, you have an E² dependence case. So what your signal look like hugely depends on the model you choose, but we've tested a number of cases, and we have some recent results here with the TeV data sample. We didn't find decoherence, otherwise you probably would have heard about it already, but we're able to set the world's by a very long way the world's leading limits on these various decoherence scenarios, and achieve sensitivity to natural Planck scale effects up to about the E³ case. I rushed over that material a little bit quick because I'm running out of time, so feel free to ask about that later. So the last thing I just want to briefly talk about was is the IceCube upgrade here. It's this is a new detector we're building. It's kind of the future of the IceCube collaboration for the next few years. So I already mentioned we have this deep core subarray within the center of IceCube, which is a more densely instrumented region for GeV scale physics. In 2025, 2026, we're going to deploy an even more dense region in the middle of this area itself. It's going to be a 2 megaton volume here, so still very large compared to most other detectors, even if it's a small part of IceCube. And within that region, we're going to put 700 new sensors, and these are a lot more advanced sensors than we've been using in the past. So rather than just a single PMT, we have certain types of units which have 2 PMTs, with looking both up and down. We also have types of sensors here which have 24 smaller PMTs, so a very large amount of active area here, and lots of segmentation for direction reconstruction. As well as these new sensors, we're going to put a hell of a lot more calibration device into the ice to really start to try to understand the ice a lot better, and really try to improve our capability as a particle physics detector. In terms of what the impact of doing this is going to look like, so as I mentioned, we're going to have a denser instrumentation in this 2 megaton core, and this large increase in photocathode density means we're going to see a lot more light from individual neutrinos, and drop our threshold down to about 1 GeV. This is an example of a neutrino event in deep core. So each of these white dots is one of our PMTs, and these yellow circles represent a hit. And so you can see here this kind of order 10, 20 maybe hits we see for a 30 GeV neutrino in deep core right now. That exact same event is going to look like this in the upgrade. So you can see a lot more light. It's going to have a lot more power to reconstruct these events. And our initial estimates are we're going to be roughly doubling our energy resolution and around a factor of 3 in our angular resolution. And overall, on average, across for these higher energies, roughly twice the efficiency as well. So we're going to be able to do a lot more precise physics for this new detector. At the bottom end of the energy scale, so this is a 4 GeV muon neutrino. This is what it looks like in deep core. It only leaves 2 hits. This wouldn't even trigger the detector. This would never make it into one of our data samples. Whereas the upgrade here, you can see this looks kind of at the same kind of scale as the 30 GeV event did in deep core. So we're going to really be able to start doing real precision physics, even down to the 1 GeV scale or so. And we're going to have roughly 4 times deep core rate overall, and about 10 times efficiency below 10 GeV. So this is really going to be a low energy precision particle physics machine. One of the main motivations for doing the upgrade is oscillation physics. Of course, the calibration of the detector will benefit the entire IceCube program, including astrophysics. But the low energy physics is mostly targeted at oscillations and also dark matter studies. This lower having all this extra light at low energy is going to really improve our resolution. We're really resolution limited currently, so this will have a huge improvement in our last sensitivities. And also these calibration capabilities are going to be essential for us to really produce trustable results with this new detector. But I'm not going to go over all the different improvements in oscillation channels, partly because we're still working on some of them. But I want to highlight one in particular, which is that we're really improving our statistics down in this region. And if you remember from before, I pointed out that this is the region where we have this kind of distortion effect from matter effects that can help reveal the neutrino mass ordering. And so, although right now we only have a roughly 1 sigma sensitivity to the neutrino mass ordering, we expect to achieve far far better than that, even within only a few years of operation with the IceCube upgrade. So for example, here you can see if for example, in the normal ordering, this prediction gets us up to around, after about 6, it's just what, 3 sigma, after about 3 or 4 years of operation, we'll achieve 3 sigma, something like this. And this is with an older version of the detector as well. The study will probably be a little better with the new detector, actually. So we're expecting to have very strong performance with the NMO for the NMO in coming years. Okay, so I think I'm out of time. I'm just going to wrap up. So what I've tried to outline here is that, as well as being great astrophysical tools, neutrino telescopes are really very potent and unique particle physics laboratories. The unique characteristics we have of our neutrino samples, so high statistics, high energy, large baselines, core crossing dense matter, all flavor detection, all these things give us a really kind of rich particle physics scope. And I've covered here mostly neutrino oscillations, but we also have, for example, dark matter programs, monopole programs, etc., that I didn't touch on here. So there's an awful lot of particle physics to be done with these detectors. We have a very broad neutrino oscillation measurement program for the atmospheric mixing parameters. We're now roughly, well, with this new 10-year measurements that we're hoping to release in the coming weeks or months, we're now for the first time becoming directly competitive with accelerators. And for some scenarios, like for example, tau neutrino appearance, and for many BSM scenarios, we have world-leading capabilities. And we're also starting to more and more explore our ability to constrain Planck scale physics as well. We have beyond the current detector, we're looking forward now to our next generation detectors. We have the IceCube upgrade, which I mentioned already, going into the ice in about 3 years from now. And this is a fully funded detector. This is definitely this is well underway in terms of the construction. And then looking further into the future, we're planning the IceCube Gen 2 upgrade. This is a proposed upgrade to the entire large IceCube array, taking it from 1 gigaton to an 8 gigaton huge detector for next generation astronomy. And that's everything I had. Thank you very much.
Thank you. Let me